first say thank you to David Abraham, for the introduction to the workshop, and thank you to the organizers of this workshop and this program for the opportunity to speak. So let me find chalk. It's been a long time since I've given a Blackboard presentation, so I'm looking for the Apple Pencil. Mostly this is all colored chalk. Right, I found a certain piece. So I want to give a series of lectures on silting theory and stability conditions. So the aim of this lecture, this series of lectures, is I want to explain what stability conditions are, sort of very briefly, explain a little bit of silting theory, and explain how silting theory can be used to prove results on stability conditions. So this is the aim of the lecture series. So first, let me give a quick sketch so let's call it section 0, motivation. Let me just explain a little bit about what each of these things is. So silting theory let's start. I say I'm considering two algebras, two finite dimensional algebras. I'm going to set D to be the bounded derived category of the algebra, usually throughout. So this is the bounded derived category. It's probably better for me for zoom to sort of work down the board, right? And sigma D to D, the shift factors, just to fix the notation. So sort of a quick summary of silting theory, I think, can be given by 3 questions. So question 1, when is the module category of lambda equivalent to the module category of gamma? And so the answer to this question is called Morita theory. And this goes back to the 1960s. The second question is, when is the derived category of lambda equivalent to the derived category of gamma? And answering this question could be called tilting theory. Which goes back to the 1980s. And the third question, I would say, is when is mod gamma a subcategory of the derived category of lambda? And I would call this silting theory. Just sort of a caricature of what silting theory is and a bit of history. Thank you for the chalk. Okay. And so why might one be interested in silting theory? So I'm just going to give a quick overview of some applications. So this is the first part of the talk is a bit imprecise and wishy-washy, and I'll say a little bit things a bit more precisely in a few moments. So first application is classify cohomology theories. In this, I'm going to mean bounded T structures. in the derived category. Right. So actually, I'm kind of lying a little bit here when I say Silting theory goes back to the early 2000s. Sort of the modern incarnation of Silting theory goes back then, but actually Silting was first observed in the 1980s by Keller and Vosik, and they used Silting objects to classify bounded T structures in representation finite in derived categories of representation finite path algebras, so ADE quivers. The reason it saw a resurgence in the 2000s is Silting objects closed the class of tilting objects under mutation. And it became clear, as I suppose is one of the key points in this workshop, and this program, I mean, with cluster theory, is in the early 2000s, one saw cluster tilting theory arise and cluster mutation arise, and Silting theory has a mutation theory, which is very similar to cluster mutation theory, and it was observed that if you mutate a tilting object, you don't necessarily get a tilting object, but you do get a silting object. And from this was also observations that in many cases, cluster tilting theory is, let's say, shadow silting theory. So you get some idea of what's going on in cluster tilting theory by having a look at some corresponding cluster theory, silting theories. Okay, so that's one half of the story that I want to talk about in these lectures. The other half is stability conditions. Now, I should say that what I'm about to say in the next 5 minutes or so comes with a big health warning, in that, so I'm not an expert in the algebraic geometry required for this, and I'm certainly not an expert in the mathematical physics of the background. So this is what I've gleaned from reading the overviews of these papers, so sort of where it comes from, and then in a few moments I'll become more precise and mathematical about things. So this goes back to the 1960s with Mumford and geometric invariant theory, and is a tool for constructing moduli spaces. So the idea is to filter objects using semi-stable objects and reduce sort of structural questions to questions about semi-stable factors. So as a representation theorist, what I see in this kind of direction in representation theories is work of Gagler, Lensing, Kursin, Lydia, Angeleri, Hugo, and so on, who've used stability, the ideas of stability to look at wild type quivers. So you get classifications of semi-stable subcategories. Every object has a filtration by semi-stables, and you can't hope to understand the representation theory of all modules in these wild type problems, but you can look at the semi-stable ones. So it's filtrations by objects you have a hope of understanding. Bridgeland stability conditions. So these come from mathematical physics. So it's a mathematical formulation of ideas from string theory. So the idea is in, say, homological mirror symmetry. I start with a superconformal field theory. And I've never managed to understand the definition of such a thing, so I'm not going to try to give one. But the idea is in physics, you have something called a superconformal field theory. And this gives rise to something called the A model and the B model. And in the A model, you have the derived category, derived Buchaya category of, in the physics setting, a Calabi-Yau threefold. And in the B model, you have the derived category of coherent sheaves on this. Kontsevich homological mirror symmetry conjecture is that these two categories are equivalent. So on this side, you have symplectic structure, which is given by, so there's something called a Kähler parameter. On this side, you have complex structure, right? And the idea is that stability conditions correspond to this Kähler parameter. So this is what Bridgeland was trying to do. And I make no real pretense of understanding this in any depth. Sorry? Yeah, this is the, okay, this is, I'm pleased to put this. So this is the mirror. So for me, or for us, so I say for us, but this is a royal us. It means for me, is that Bridgeland stability conditions are continuous versions of bounded T structures. Why this is will become apparent. And so the space of stability conditions which is written as stab D, is a geometric invariant encoding all the cohomology theories. This is actually a lie, so it's not all, okay, but most, right? So the idea is that we can get a geometric invariant out of the homological algebra of the category. So we have some geometric way of understanding the homological algebra, and that's what Bridgeland stability conditions gives us. And this space allows us to understand how different T structures are related to one another, as well as geometric problems. So this is the motivation I'm coming from. So I want to understand the homological algebra. Okay. So now I'm going to be a bit more precise from now on. This is just a motivation. On the back of this page. So in this lecture, I want to explain what are stability conditions. Just see if I can find a clock. Yeah. That's right. So I'm going to try and keep the numbering going, but if it fails, then I might just abandon it. So A, an abelian category. A stability function on A is a group homomorphism usually denoted by Z from the Grothendieck group of A to the complex numbers. So the Grothendieck group of A is given by, so is generated by, so it's a free abelian group generated by equivalence classes of objects up to, if I have a short exact sequence x to y to z to 0, I have the equivalence class of y is equal to the equivalence class of x plus z. That's the relations. So it's sort of an abelian group approximation of your category. So a stability function is a homomorphism z from the Grothendieck group to the complex numbers, such that for any non-zero object theta A in A, we have Z of A. So this is the last time I'm going to write it. So I'm always going to write Z of A and abuse notation and not write the equivalence class, is equal to M of A E the I pi of A, which is which has to sit in the in a strange upper half plane, which is R e to the I pi theta, where R is strictly bigger than 0, and so phi runs between 0 and 1. So let me maybe it's better to draw H. So H looks something like this. It doesn't include 0, doesn't include the origin, doesn't include the positive real line, includes the whole upper half plane and the negative real axis. So that's H. Okay. This, so the modulus of Z of A is the mass. Yeah. This, yeah, yeah. I thought I was writing quite big, but it looks big here. Mass of A, I tried to write bigger. So mass of A is here, and the phase, this normalized argument of Z of A is called the phase of A. So an object A in A is semi-stable. Is this big enough? With respect to Z, but we usually omit the Z when we say this, if each sub-object satisfies the phase of the sub-object is smaller than equal to the phase of A. Okay, and this can also be formulated in terms of the factor object. So if and only if each factor object satisfies double check. Switch my order and switch my sign, getting something wrong. So here. Okay, so this is the definition of a semi-stable object, and one can check that one of the consequences of this definition, it means that between semi-stable objects, there's no non-zero homomorphism from one of big phase to one of smaller phase. So it puts a directionality on your homomorphisms. So this is what semi-stability is doing. So if I have Z from the Grothendieck group of A of the complex numbers, it's double prime. Yes, should be. The quotient object is double prime, the subobject is single prime. So this is a stability function. So a Harder-Narasimhan filtration, which I will know from now on always abbreviate HN filtration. Of a non-zero object A in A is a finite chain of subobjects starting at 0 going up to A with the property that whose factors Fi equals Ai over Ai minus 1 are semi-stable with respect to the stability function Z, with the phases of the semi-stable objects strictly decreasing. It's not guaranteed that such a filtration exists. So if such a filtration exists for each non-zero object of A, then we say Z satisfies the Harder-Narasimhan property or the HN property. So the idea here is that with a stability function, we get these filtrations, and these filtrations with whose factors are semi-stable, and which satisfy nice homorthogonality properties, which simplify how we can understand the behavior of these objects. So a remark. So one, if A and B in A are semi-stable with phi of A bigger than phi of B, then there are no homomorphisms from A to B. The second, which will be relevant in representation theoretic context, so any group homomorphism, where am I? So any group homomorphism satisfying this property on a finite length category, so any stability function on a finite length category automatically satisfies the Hn property. So if you're dealing with module categories of finite dimensional algebra, this condition here, the potential non-existence of Hn filtrations is not an issue for you. Any stability function on a length category, where length means each object is Artinian and Noetherian, satisfies the Hn property. In fact, because in the length category, Artinian Noetherian means every object has a composition series whose composition factors are unique of the permutation and isomorphism. This means that specifying a stability function on a length category is equivalent to specifying a stability function on the simple objects. So it's determined by its action on the simple objects. So in such a category, stability function is completely determined by its values on simple objects. Really have forgotten how to write at the blackboard. Okay. So where was the right. Okay, so let's give a quick example. There's a joke I'm often fond of saying is that Jan Schur always used to complain about examples being type A3 and wish people would do something different. So I'm going to do something different. Let's take A2. So here I'm going to have the simple at 2, projected at 1, and the simple at 1, as this is its AR quiver. And I'm going to give 2 stability functions on it. So let's put Z of S1 up here, and Z of S2 up here. Try and do the parallelogram. Z of P1 here. And we see here that there's, So for that here S1 and S2 are semi-stable, but P1 is not, because S2 is a subobject of P1 with bigger phase. And let's do the same picture where I instead switch S1 and S2 around. Again, set the P1 here. So now S2 has smaller phase than P1. So this is semi-stable. And this is supposed to be S1, sorry. S1, which is a quotient of P1, has bigger phase than P1. So in this stability condition, S1, S2, and P1 are semi-stable. So in general, I can choose what I want for the value of the stability function on the simples, and then the Jordan-Holder filtration of every other object determines the value on those objects. And then you have to have a look at what you get to determine whether the objects are semi-stable or not. Okay. I should say in this one, for example, so the HN filtration of P1 is simply this one where I'm writing. So this is, each of these are short exact sequences. So this is actually the Jordan-Holder filtration of P1. That's the HN filtration. So now I'm going to go to, so that's stability functions on abelian categories. So let's move to triangulated categories. So D are triangulated. The shift functor is again sigma. And I'm going to say E, a subcategory of D, is extension closed. If whenever I have a triangle E prime to E double prime to sigma E prime, if this is in E and this is in E, this implies that the middle term is in E. And later on, I'm going to introduce it, but I'm going to need it a little later, but not quite yet. The star product of two subcategories is equal to the set of objects D and D, such that there's a triangle of the following form, with the first term in E1 and the second term, the third term, sorry, in E2. And by the octahedral axiom, the star product is associative. So from now on, whenever I write star products involving more than two subcategories, I won't write the brackets. Okay. So this brings me to the following definition. So a slicing P on D is an R indexed family of additive extension closed subcategories such that the following conditions hold. For each element of the real numbers, the slice of 5 plus 1 is the shift, the slice of phi. Two, if phi 1 is bigger than phi 2, P1 is in P of phi 1, P2 is in P of phi 2, then P1, P2 is 0. And the third condition is that for each non-zero element of D, there exists a tower like this. Well, when I write A to B to C like this, I actually mean there's a distinguished triangle like this. So the wiggly arrow is going back to the positive shift. So there exists a tower of this form with Pi in the slice indexed by phi I, and these phi's strictly decreasing. Okay, and this is called also called an HN filtration. So if you look on the board above, you see precisely that this here is. So what is this capturing? So this is something specific to triangulated categories. This is trying to capture the first part of this remark up here. And this last axiom is capturing the existence of the HN filtration. So a slicing is trying to build up the components of the stability function. So I can. So let me give two quick examples. So examples 1.6. So now I'm going to give, so how best to do this? So I'm drawing, so I'm going to take DBKA4, and out of laziness, I'm not going to draw the arrows in the kind of writing quiver. You're supposed to remember where they are. And I'm not going to label the objects. I'll just indicate where somehow the most canonical module category or heart sits, even though I haven't defined this yet. So here would be, say, mod K4 with the linear orientation. So I'm going to try and use some different colors. Green is bad. So I think it's worth seeing these. So let's index this by, so this is P of phi 3, P of phi 2, and P of phi 1 with...
Yo vi dos chiquitos que estaban sentados encima, pero no se quedaron pegados.
1 bigger than or equal to phi 1, which is bigger than phi 2, which is bigger than phi 3, which is strictly bigger than 0. Okay. So I defined it on this module category region. Now, because everything in the derived category is a shift of this, this determines by this first axiom up here, the slices for all the others. So that's so these are the different shifts. You get a slicing. And for example, you see here that this object here has a hard and narrow symmetry filtration, which we'll probably have. Maybe it's better to do. It's going to have this one, and this one has its factors. Okay, so this is an example of a slicing on DB A4. I want to give a second example. And then I will finish with a definition of a stability condition and then call it a day. So the second example, still on type A4. Something like this. So the advantage of a Zoom talk is you can prepare these pictures in advance. I'm trying to keep the colors the same, so that's why I'm looking for them. So this is also a slicing. If I've not made any mistakes. Okay. With the same conditions on these guys. There's something interesting about these. There's an interesting difference between these two, which I'll get to a little bit later. Or maybe I just give the punchline now and explain it. This one comes from a stability condition, that one doesn't. So this is, so it comes from a stability condition. Does not come from so Karen, do I have, I think, 2 or 3 minutes to give the definition and then finish? Is that okay? Yeah, and if I'm just giving the definition, then I stop and we discuss more about it tomorrow. So a stability condition is a per sigma equals Z P Z is a group homomorphism called the central charge. And P is a compatible slicing. i.e. for non-zero objects D in a slice P phi, we have Z of D is equal to its mass so this is the mass, the phase. So each object in the slice P phi must have normalized argument equal to phi. And we say that P phi is a set of semi-stable objects of phase phi. So if this is a stability condition, each P phi is abelian. So this is what fails in this example. So these categories are, this blue one here isn't abelian. And so we can say ZP is locally finite if each P phi is length. So it's a finite length category. And so just doing this space here, stab D is equal to a set of locally finite stability conditions. On D, and that's a subspace of group homomorphisms from K0 to Z across the space of slicings, which I'll say more about tomorrow. Okay, so today's lecture, we defined the stability function on the abelian category, talked about Harder-Narasimha infiltrations, slicings, and eventually got to the definition of stability condition. In the next lecture, I want to talk a little bit about the topology of stab D and how one uses T-structures and tilting to move around the stability manifold. Thank you. Sorry for overrunning a little bit.
Thank you very much for your very nice and clear lecture. There were no other questions in the Zoom, and then I think in the interest of having the 10-minute break, I prefer questions to be asked directly to David or being written later in the chat. Hi, David again.